Try.
Whoa.
That was.
Can you do that again?
I will.
That was.
So we're covering related rates, also known as word problems.
Ew.
Oh, shut up. They're not that bad. They do involve a lot of different scenarios. I like the ones that tie into the real world, but the first couple we'll do don't have any tie to the real world. And we're going to go slow. The slower we go, the more likely you are to get this into your brain. So we'll talk about related rates. We're going to solve real world problems using the 9-step approach. Yeah.
Why not?
That wasn't meant to be a joke. There's 9 steps.
Yeah, I was being reactive to there being 9 steps.
Is that like your defense mechanism? You laugh? Like if somebody threatens you with violence, you just laugh at them?
Good one.
That's a good response. We'll kill you. Yes, Sean.
Are there other step approaches? Or is it only the 9-step approach?
I'm sure someone has developed maybe a 10-step approach. You know, it's been doing it a little bit longer. They got an extra step just for a little oomph in there. But mine's 9.
Okay.
You could probably do it in 8. You can do it wrong in 1 if you'd like, but yeah. And then of course you should enjoy spicy foods.
I can't.
Yes, you can.
I think the mild things that beat ups are spicy.
What's that?
What?
The mild things that beat ups are definitely spicy.
Oh yeah.
What's
I get
Thank you. They're not mild.
They're not
The
really
mild
mild.
wings at Buffalo Wild Wings. Sorry, I do not like beat ups. Okay.
That's okay.
Buffalo Wild Wings. Those things are really spicy.
I don't eat at Buffalo Wild Wings. There's a better place by my
I
house.
literally like drink like
Whoa.
4 pounds like in a meal.
60-cent wings tonight.
Okay, so
Oh,
everything we've done so far has involved y prime, also known as dy dx, the derivative of y with respect to x, okay, where x is the variable. We're going to change that now, and everything is going to be related to time. So when we did implicit differentiation, if we took a derivative with x, everything was fine. We just treated it normally. If we took a derivative with respect to of y, we had to stick on that y prime. With related rates, since everything is related to time, you got to stick something on the end of everything. You take a derivative in terms of x, you got to stick something on the end of it, and we'll talk about what those things are. But again, everything is with respect to time. So we'll start with this one. We've got a differentiable function. That's important to get in the habit of recognizing in problems. Differentiable function means it's differentiable. If it's not differentiable, then stuff starts to break down. And I also want to remind you that if it's differentiable, what else is true?
It's continuous.
Good, it's continuous. That's important. But if it's continuous, it can be differentiable, but doesn't have to be. Okay, good. That comes up a lot.
Is that like if it's, like, what's an example of something that's continuous but non-differentiable?
Absolute value.
Absolute value. What about like is a constant technically differentiable? Okay, because it's just going to be 0.
Yeah. Okay, so suppose x and y both differential functions of t and related to the equation, blah, blah, blah. So we got a parabola. Opening up, shift, who cares? And we have some conditions here that we're going to use at the end. So first things first, I took the derivative using time as my, with respect to time I should say. Okay, I'm going to take the derivative of y with respect to time and the derivative of x squared plus 3 with respect to time, which means that both of those things are going to have something on the end of it. And we're going to get away from primes now because we're going to have to use this Leibniz type notation to keep track of everything. Okay, so what's the derivative of y with respect to time?
2x.
What's a derivative of a variable? 1. Okay, then we have to stick something on the end of it. We'll get to that in a second. What's a derivative of x squared plus 3? 2x. But then we have to stick something on the end of it. That something that we stick on the end of it is that dy dt and that dx dt. So we were sticking dy dx on the end of it, dx dx on the end of it, which was 1. That's why we didn't bother with the x's. But now everything is in terms of t. Okay, so we get that. How many unknowns in that last equation? 3. Right. Basic rule of algebra. If you want to solve an equation with a bunch of unknowns, you have to have one less than the number of unknowns in order to be able to solve it. In other words, if I have 3 unknowns, I need to know 2 of them, at least 2 in order, well, I gotta know 2 to solve it. If you look at the last line of our given information, we know that find dy dt when x equals 1, given that dx dt is 2, and when x equals 1. So we know what x is, we know what dx dt is, so we can solve for dy dt. Plug and chug, you get your answer.
So,
Go ahead.
so when you plug in for that equation, so it would be like dy over dt equals 2 parentheses 1 parentheses 2.
Yes.
Okay.
So that would give us 4. Did I do that right?
Yeah.
Yeah. So we should get an answer of 4. What's that? Excellent, I was hoping somebody would say that. That's the single biggest mistake that people make when they're doing related rates. You can't plug things in early because we're looking at this taking place over all time, every possible time, because we don't know what time is. So we take the derivative, yeah, it's gonna get worse. We take the derivative and then we look at one particular moment in time. The particular moment in time we're looking at is when dx dt equals 2 and x equals 1. Okay, I commonly call that a snapshot. And it'll make more sense when we get to the real problems. Okay, Mary?
So in the, like, under the solution, the y, does it go to the, like, dy over dx, dt?
The y goes to a 1.
Okay, okay.
And then it's just like when we do an implicit, when you took the derivative of y, you got 1 y prime. So instead of a y prime, we're now writing dy dt.
Okay, and then for the 2x,
Yep.
you just found the derivative of the other thing?
The stuff in the bracket.
And then you put it in front of the,
Yeah, you stick the dx dt on the back end.
okay,
Okay.
that's it?
So, with the dy dt and the dx dt, is it kind of like the same thing? Well, it's a derivative, so when you take the point like dx over dt equals 2,
Mhm.
like you said, it's a snapshot. Is it kind of like, is it going to be a slope at that point, or is it going to be?
In this particular equation, it's, yeah, in this example, in other words, I'm asking at the time that the slope,
is x equals 1 and
at the location x equals 1, when the slope is 2, then what is the, yeah, don't think about it too much, your head will explode. Okay. Just go with it. I'm not gonna read to you because I think you can handle it, but the problem we just did is what's called a naked related rates problem. It doesn't tie into anything in the real world. Okay, it's just an equation, you grind out the derivatives, you plug in what you know, you solve for what you don't know. They don't pop up very frequently, but they do occasionally. Okay, we're gonna look at more exciting things, like what happens if you have a leaky container, or you're filling a container. You got cars crashing into each other, you got people falling off of ladders, sliding down ladders. We'll slide down a ladder to the side. You ever been on a ladder when it falls off a building?
No.
You pretty much got 2 options. You either slide down the building this way, or it slides down this way. Okay, this one is much more horrific, because there's nothing you can do except try to grab onto the siding, and it's horrible.
Who do you?
I have fallen off of a ladder this way,
Mr. Grassy's
with
falling
2
off
gallons
the
of paint in my
twice.
hand. What?
I said Mr. Grassy's fallen off the ladder twice.
Yeah, he messed himself up pretty bad too.
He got his like tailbone.
Broke his heel.
Eat a lot of
Does
potatoes.
that have
9 steps. Number 1, draw a picture.
Well,
That's a good step.
Yeah.
I'll remember.
And by the way, that picture should be related to the problem, okay? If the problem involves inflating a balloon, don't draw a picture of a dog. It doesn't make any
Holly's at the
sense.
door.
We've got our friend.
It's open.
The handle didn't turn, so maybe you got it?
It's open. Be sure to label the picture. Okay, it doesn't have to be a perfect artist rendering, but it's got to be something that resembles the situation that we're dealing with. Step 2, define the variables. Assume that the person reading your problem has no clue what's going on. that they don't know simple things like R is radius, V is volume, A is area. Okay? Define all of that. And sometimes you'll change it. I mean, I might do a problem where I define the distance a certain car travels as X. You might define it as A. So you want the reader to be able to pick up your problem, and it makes perfect sense based on the work that you've done. What do you know? What are you looking for? In other words, what's your given information and what am I trying to solve for? Okay, we good? Step 4, general equation. Very important, the stuff in green. Do not plug and chug yet. And once we go through this 9 steps, all I've got for the rest of the slideshow is examples. And these examples will start to make sense as we apply the 9 steps to them. You'll understand why these are relevant and why I chose these 9 steps. Take the derivative. Now, the nice thing about this is 99% of the time the derivatives are really simple. Okay? It's like taking the derivatives of squares or the derivative of something linear. You know, the derivative is not the hard part of the problem. Step 6, we get the snapshot. So that's the moment in time we're looking at. So for instance, if I'm falling down the ladder, I'm going to have different situations at different times. As I start to slide down that ladder, my speed will change. So I might want to know, well, how fast am I going when I'm 1 second from the ground? How fast am I going after I've started to fall for a second? When am I going a certain speed? You know, so there's all kinds of different things that can be applied. That all takes into account in the snapshot. And that's where you do all your plugging and chugging. Step 7, solve. In other words, plug in what you know from up here in step 3. You'll have one variable left. Solve for that missing variable. You got your answer. And then 8 and 9. Does your answer make sense? You might be able to answer that. You might not be able to answer that. But if you get in the habit of asking yourself that question, it'll help. So, for instance, if you're filling a balloon, which I have an example, you might not have any idea what a reasonable volume is or a rate of volume change to fill a balloon. But if you're calculating how fast you're traveling as you're falling down a ladder and you get an answer like 843 miles per hour, you're probably not going to fall down a ladder faster than the speed of sound. Okay? Yeah, and I get all kinds of strange answers. I mean, I have people do calculations where they find the weight of something, you know, the weight of a basketball all of a sudden is 14 metric tons, you know, so take 2 seconds and make sure this makes sense. And then the last one is units.
Would you purposely make problems that don't make sense though?
No.
Like if you just like put like a random like, because you can change like the topics of them easily.
Yeah.
Like you could put a basketball to like a metric ton.
Right, I could have a basketball that weighs
A
14
lead
metric
basketball.
tons.
Yeah.
Yeah. But I won't. Everything's going to be fairly reasonable. But again, like I said, you might get some problems where you're not going to know if that answer is reasonable or not.
If there was like a AP question on this,
Yep.
is there a point for every single one of those?
That's a great question. And when we start doing these types of problems, there's almost always at least one related rates problem in the free response part of the test. It depends on the year. I mean, there are some years when you get a point just for putting the correct units on there.
Yeah.
Okay. There are other years where they don't care what the units are. It's just not relevant in the point. So it depends on how they
What
set
kind
up
of
their
mood they're in?
exactly, and what their emphasis is and all those kind of things. Okay, we good with the 9? You might want to put a box around that because you're going to be using it a lot, or highlight it, or maybe a puffy cloud with some arrows and a star, or whatever works for you.
Cut it out, put it on your forehead.
No, you can't put it on your forehead. Put it on someone else's forehead.
Get a mirror.
Make a t-shirt out of it.
There you go. Print it upside down,
Then how would you see it while you're
and then sell it to all the students.
Where when you use
Yeah.
that down, you
Wait,
put it
somebody
Write it
else
on
put
my-
it in physics.
Yeah,
Something
like
like-
write
don't
it
they
on
do
my-
that?
write it
Do they
in.
still do that in physics?
No, they just gave us an equation sheet.
Oh, back in the old days, they made
What happened?
T-shirts. where they had them upside down on there, and you would have to.
Yeah, I have
you
one.
take the test.
Physics, you guys make a cheat sheet, a full piece of paper.
Okay, so here we go.
Front and
We're gonna
back.
inflate a balloon. Air is being pumped into a spherical balloon, so that you're not doing like a what are those? A balloon animal type balloon. It's not a cylindrical balloon.
No.
It's a spherical balloon. At the rate of 4.5 cubic feet per minute. Find the rate of the radius, or sorry, rate of change of the radius when the radius is 2 feet. A lot of information in that first thing. And from all that information, our job is to figure out what each of those things means and how it fits into the 9 steps. Your pictures don't have to be this beautiful. You'll see when I go through the 9 steps how simple it can be. Okay, we ready?
No.
Okay. How about now? And now?
I just got like a circle.
Hmm?
I just did a circle.
That's all I did.
Okay.
Just a big circle and a small circle.
Okay, step 1, draw a picture. Well, I reduced my 3-dimensional sphere into a circle with a radius. But I don't want to assume that the person reading this knows what a radius is. So in step 2, I define my variables. I'm going to be using r for the radius and v for the volume. Because again, remember that's 3-dimensional. If you want to draw a 3-dimensional sphere, knock yourself out. Shade it. Do whatever you want. Get all crazy.
Make it out of triangles.
You could. Really smart. And let the area of each triangle go to 0. Limit as triangle approaches 0, but the number of triangles approaches infinity.
Infinity, yeah,
Yeah,
there's a lot of
that's a
triangles.
calculus concept there. All right, this is in my opinion, this is the hardest step in all of these problems. What do we know and what are we looking for? So it says air is being pumped in a spherical balloon at a rate of 4.5 cubic feet per minute. Cubic feet per minute is what?
Unit.
It's volume, right? So this is a volume, and it's a rate. Now, I would recommend when you're doing related rates problems that you get yourself a highlighter or a red pen or something and underline important terms in the problem, like rate. Pregunta.
So that's step 3.
Oh yeah, that's
What? Okay, first problem was switching to Keynote. Screwed up my numbers. All right, this should be a 3. Thank you, Sam. So that 4.5 translates into dV/dt. It's a rate of change of the volume. The problem then, if you go back to the problem and read, it asks you what is the rate of change of the radius. Okay, so I'm looking for dr/dt. When am I looking for dr/dt? When r equals 2. Almost every related rates problem, when you do the what are you looking for thing, is going to take the form of something equals question mark when something else happens. And that something else could be a measurement like the radius in this case. It could be a time of day. It could be other conditions that tell you when the snapshot is happening. Okay? How are we doing so far? Okay, good. Step 3/4, general equation. What's a general equation?
something that you don't plug and chug into yet.
Correct. What are we doing? You're thinking too much. What's my general equation?
The volume of the thing. but I
Volume
don't-
of the thing, and what is that thing?
Balloon, but I don't know what that is.
Good, you don't have to remember it. On the AP test, when you get into 3-dimensional models, they'll give you things like that.
Oh, that's money.
Why can't
Or
they give
third
that to us?
hierarchy.
Yeah.
What do you mean in the beginning?
Like you gave it to us now. Do they give it to us at the beginning?
Yeah, they'll say,
Okay.
they'll say in parentheses, volume of a sphere is 4/3 pi r cubed.
No, they wait for you to complete steps 1 through 3.
Yeah. This problem is on page 2, and then on page 47, they go, oh, by the way, problem 2.
No, as soon as you complete it, the magic mark.
Right. Now that you're done crying, turn back to page 2 and the volume of the sphere is blah, blah, blah. Ha, 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 ha.
I wanted to.
LOL. Okay. Oh, good, we're back. Number 5. Take the derivative. All right, I'll let you do that.
Bless you.
Gesundheit. Gesundheit?
I'm guessing in bless you that or what language?
No, I don't mean bless you, it means have a good life. It's German.
The reason people say bless you is actually really interesting.
I don't say bless you.
No, I mean like the reason some people do. There's a couple theories as to why people started doing it. One-
Wait, we don't have time for it right now. Sorry. I don't have time for a history lesson. What's the derivative of v? 1
1.
dv dt. What's a derivative of 4/3 pi r cubed? I'd love to remember the formula. It's so sad. 4, that's a good start, because the 3 comes down, multiplied by 4/3, it'll be 4 pi r squared. Where have we seen that before? Oh, is it?
No, I guess circumstantial.
It's the surface area of the sphere. So when you take the derivative of the volume, you get the surface area.
It's like the slope of the.
Completely irrelevant to the problem. Okay.
Why do you add d or dt?
Why'd you add the?
How'd you?
Is that like to notify that you took their derivative?
Yeah.
Okay.
Because again, remember, everything's in terms of t. So anytime I take a derivative of something other than t, I've got to stick a something on there. So if I take the derivative of smiley face, let's do smiley face squared. Take the derivative of smiley face squared, I'm going to get 2 smiley face, d smiley face dt. If I take the derivative of Sam cubed, I get 3 Sam squared d Sam dt.
So that's the respect or radius.
Yeah, it's
with,
you're showing respect.
radius with the respect to time.
Give it some respect to the r.
Well, no, respect to the t.
Respect to the t, right?
Yeah.
Yes, Sam.
Do you treat pi there as like a coefficient? Not as a.
Tree, I'm sorry, what?
You treat pi like it would be coefficient.
You say number.
Huh?
You say number.
Okay.
Yeah.
Which is
It just sits out in front and does nothing.
crazy.
Okay.
Okay. Step 6, snapshot. Now we can get all crazy with this information we know. We know what dv dt is. What is it, 4.5?
Yep.
Yeah.
We know what r is. 2. So we can solve for dr dt. Killing me.
We should just call
Wow.
it the moment of.
Wow, that was like a joke grenade.
We should call this.
You okay?
I think.
Yeah.
With AP, be petty and take off points if you don't write units in your equation.
You don't need any units until the end.
Until the end?
Yep.
If you need
That's
it.
I like math better than physics.
I'll show you at the end how there's a nice easy method for figuring out the units that's surefire,
Okay.
where you don't have to worry about it. Pretty much it tells you exactly what the units are supposed to be.
Okie dokie.
Yeah, so plug all that in, solve, you get an answer here. Yeah. Probably need your calculator for that because there's a pi there. I'll trust that you've done that. I'll trust that my pen works too. There we go. Solve. There we go. 0.09. 3 decimal places is the standard in AP. Why did I only go to 2 decimal places?
I'm guessing one of them tapped off.
If you actually did the calculation, it would be 0.090. You can drop that final 0. Does that answer make sense? Do you have any idea what a reasonable change in radius is when you're inflating a spherical balloon?
Small.
I do not either, but I'm confident enough in my mathematical abilities that I'm gonna go with that.
What's not gonna be a big number?
What if it's a really big sphere?
That's only a couple.
It doesn't mean that the change is big.
Still gonna be, I still feel good about it.
Unless we're using like a pressurizer.
Okay, this answer seems reasonable.
Is that?
Do you actually have to write that each time?
No,
Okay. I just wanted to clarify.
here's the secret to finding units. What did I solve for? Well, I solved for drdt. My units need to match what I'm solving for. So if I'm solving for, let's say, volume, my units need to be volume. If I'm solving for the rate of change of the radius, my units have to match. So all you do is the following. The top is radius. What units were our radius what units was our radius in? Feet. The bottom is time. What are our time units? Minutes. Feet per minute. Done. If you solve for, let's say, a distance, then what units were your distances measured in? If you solve for dv dt, well, that would be the volume over the time. Okay, so use what it is you're solving for to get that final answer.
Mr. Eady, I think I messed up somewhere along the way. My numbers were off.
Let me go back,
Yeah, my numbers were actually best.
unless I screwed up. Wow, that was a big jump. Okay, so we got that, right? Okay. Then plug in 2 for R and 4.5 for dv dt. Now you found it?
Mhm.
Okay, what'd you do wrong?
I combined 6 and 7 into one step.
Ah. Okay, so we're good?
Yeah.
Beautiful. Let's try another, shall we?
It's the board says no.
We'll take a cone. This you like cones?
Ice cream cone.
Yeah, there you go. Think of it as an ice cream cone. Life is better now, right?
It's melted ice cream, it's water.
This you won't need to remember. They'll give you this. Alright? So that's one less thing to worry about. The reason I want to do a cone is because a cone commonly has a little bit of something that pops up that you're not going to enjoy, but you need to see it. So we'll take you through the steps, and then you'll understand what I'm talking about when we get to that point. Okay, so give you a second to write that down.
Oh, I thought we were still talking about ice cream.
Shape of an inverted right circular cone.
Yeah.
So what
There's
is
a lot
that?
of multisyllabic words in
What
that
is,
statement.
what does that puppy look like?
Well, it's inverted, so it's upside down.
Upside down.
It's right, meaning the cone isn't slanted. And it's circular, the base is circular, which is kind of redundant because all cones have circular bases. There's no such thing as a square cone,
What about
because
the
that would be a
traffic one?
pyramid.
Wait, how do you have a right to
What about the traffic one?
Kevin, looks
What
like
about
a-
the what?
It looks like an
Traffic
ice
Oh,
cream.
traffic
cone.
ones are still cones, they're just not inverted.
No, but they have.
Casey, question?
Oh, what happens if you have, okay, well, will we have, 2 different units for time ever?
No. Are there in this problem?
Like light years and stuff.
I don't think so.
Light years and seconds. Right. Right. You throw a ball at your brother, traveling at 4 light years.
And see
Which
how
is a
many-
unit of time,
See how many
strangely enough.
seconds you can get
Yeah.
into the ER.
That's a big mistake that Star Trek always makes. They use light years as a distance, or as a speed, but it's actually a distance.
Distance.
Yeah.
Like, yeah, do light years per second.
Do you write them any complaints?
Oh yeah, every week. I'm that guy.
What about the new one?
I just
How
have the
did this
same
Star
email.
Trek
I just
thing
copy
go
and
up?
paste over and over again. Yeah. And I track down the producer when I go to the conventions with my Klingon costume on and my Vulcan ears. Excuse me, you continue to use light years.
You'd think you'd
Yes.
get it by now.
What does this look like? 'Cause it says a cone.
It's an
it
ice
also
cream
says,
cone.
Go back.
Like how? Like how do you?
Inverted, upside down, cone. You know what a cone looks like.
Yeah.
Right.
kind of.
That's not to say that we won't have problems involving regular cones. For instance, they store salt, like road salt, in cones. So you may have to calculate how long it's going to take to fill a road salt thingy jobber.
Think of a jobber.
Okay. This problem, and a lot of problems like this where we're talking about fluids, whether you're filling a pool or you're pumping hydraulic fluid into lines, the substance that you're working with is relevant. And we're working with water here. Why is it relevant? Because different substances behave differently. Thank you. Density is what we're talking about. That little conversion, the last thing at the bottom that's in parentheses, is important. Is that something you need to memorize? No. But it is something you need to use because we want everything to be in the same units. Okay, we can't combine gallons and cubic feet in the same problem. So we're gonna have to convert gallons into cubic feet. It's not a big deal, but it is somewhat relevant.
The conversion is needed.
Conversion is what?
Wheat.
Great.
Wheat speak.
They're delicious. No, just smile and nod. It's what I do. It works pretty well.
Guess you're eating those like lead.
I know what it is, yes.
What?
Wheat speak.
All right, we good? There's it. There's the cone. And when I drew it, I chose some arbitrary depth. It doesn't matter. But I called the height of the water h, and I called the radius of the water r, which is different than the height and the radius of the cone that's containing it. This will work for any point in time. The cone, however, is going to be constant. It has a height of 12 and a base radius of 6. That becomes relevant later on. Step 1, check. Step 2, what are my variables? R, which is radius of water. Good. And H, Mary? Height of the water. Good. I was feeling fancies in my panties, so I wrote H2O. This means water, by the way, kids. I didn't know if you knew that. I don't know. Have you had chemistry yet? Oh, okay. Well, you'll learn that eventually, that H2O is water. 2 hydrogens, 1 oxygen.
Well, dihydrogen monoxide.
That's what I said, yeah. Here's what I know. Here's what I'm looking for. Okay, so dVdt, it says it's being pumped into the tank. So we're filling a tank, which is different than emptying a tank. That comes later. 10 gallons per minute. Gallons is not acceptable, so I converted that into leet speak. That just made his day. We're going to be talking about that at the dinner table tonight. I converted gallons into cubic feet because that's our units of measurement for volume.
Sarita, we have to laugh forever.
Yeah. I forgot we're recording. I haven't sworn yet, have
Wait, we're
Earlier
recording?
in the year, I think you did.
I? dHdt is what we're looking for because it says approximate the rate at which the water level is rising. So the height is getting bigger, and it's a rate, so it's a dHdt. When h equals 3, that's going to be our snapshot. So we got 1, we got 2, we got 3. General equation I gave to you before, which is that guy. What are we doing? It's out of control now.
Oh no.
I'm going backwards.
Punch it.
Don't go too far.
Okay, good. Yeah, there. Uh-huh. Yeah.
Don't spoil it.
All there is.
No, that's the last one.
Wait till you watch this.
Okay, we're good.
Hey!
There's the equation. 2 ways to solve this problem. They will both get you where you need to go. I think, this is just my opinion, that one is easier than the other. I'll show you both because the other one might work better for you. It's entirely up to you which one you want to use because they're both going to get you where you need to be. We're going to do a little similar triangle action going on there because we introduced two variables into this problem. We've got an R and we've got an H. And we don't want to do two variable problems whenever we can avoid them. Okay, that's for my method. If you want to do two variable problems, you can, and I show you how to do that at the end of the first method. I'll take you through the first method. So remember back in geometry when you did similar triangles and you hated every moment of it?
Yeah.
This is one of the few times where that actually pays off. So I have similar triangles there. In other words, I chopped the cone in half,
Oh.
and I've got a radius of the cone, the radius of the water, the height of the water, and the height of the cone. And I'm sure if you remember from geometry then, we would set up something like the height of the water over the height of the cone equals the radius of the water over the radius of the cone. Or, the height of the cone over the radius of the cone is equal to the height of the water over the radius of the water. You have a couple different ways to set it up, whatever works for you. Why are we doing this is the first question you're probably asking yourself. Why are we doing this?
To get height of one.
Yeah, we're going to get rid of one of the variables using this information. And it looks something like that. Okay. So I did radius of the cone over height of the cone equals radius of the water over height of the water. Did a little bit of cross multiplication and solve for R. Why did I solve for R? Why not solve for H?
We're given.
Casey?
Because we know the H.
Good.
Because it's the
And depending on the problem, you can solve for either one. I could take this and easily solve for H and sub it back in. But we have information about dH dt, so we'd like to work in terms of H. Are you okay? So far?
Wait. Can you go back really quick?
I don't know. Maybe not. Oh, my God. Thanks, Sam.
Sam ruins everything.
He strikes again.
Okay.
Ah. Woo. Now notice what I did. Well, you tell me. What did I do?
Why is there another H?
That's a good question. And if we can answer that, you can answer my question. What did I do to get to there?
Just plug them.
Say again, Kev.
You plugged the R into the original equation.
Beautiful.
Oh.
I don't want to work with two variables, so before I start taking a derivative, I got rid of one of the variables by plugging in that stuff we got from the similar triangles. Now we got a nice equation that when and hopefully you can see, and I think I probably did the math, that'll simplify real nicely. Nicely? Real nice. Is that right?
It will simplify
Nicely.
nicely. It's an after.
My English is horrible. Okay, so we'll get pi over 6h cubed. Yeah. And that's easy, right? You can take the derivative of that, because I think that's the step we're at, aren't we? What are we on? Had a picture, define the variables. What do we know? What are we looking for? General equation, is that 5?
Yeah.
Yeah. 6, take the derivative.
Wait, 5.
So 5 is take the derivative.
5 is take the derivative, okay. You think I know my own steps. Okay, so let's take the derivative. What is the derivative of that equation, Alex?
Oh,
What was it, 1/4?
Yep.
1/4 pi h. 1/4 pi h3. Pi squared.
Pi squared. You forgot one small thing because we're doing related rates.
Times the d
Yeah,
dh over dt.
perfect. Okay. Everybody good with that? Brought the 3 down. 3 pi over 12 is the same thing as pi over 4. So you wrote as 1/4 pi times h squared, reduce the power by 1. And because we took a derivative of h with respect to t, then you got to stick a dh dt on the end of that. How many unknowns in that equation, Sam?
Two, three,
Which one? 2 or 3?
three.
3, good. And in order to solve that, we need to know 2 of the 3. Do we know 2 of the 3?
Yeah.
Which ones do we know?
Um,
I don't remember.
d over dt. I think it's d over dt and h.
Okay, I'll trust you. You have an honest face. Is he right?
Yeah.
All right, good. Okay, so this works for any point in time that you're draining that, no, filling? We're filling the cone. But now we want to know, what about a specific moment in time? And it might not be a time, it might be a specific moment in time when this is true. And I think it's when h equals 3? 3, yeah? So then we plug and chug. So now we do the snapshot, which I believe is 6.
3.
Oh, steps.
Question?
Yeah, is there any other way you can go about it to find the things that you have to plug in at the end, or will it not work? Because if you take anything without the respect of time, then the units won't match up. Do you kind of get what I'm saying?
I understand what you're saying. I'm trying to think of an eloquent way to answer you. Yes. In some of the problems we're gonna do coming up, we do what I call a sidebar, where the similar triangles is kind of a sidebar. We need information, so let's stop what we're doing, go over here, do some calculations, get what we need, come back to the original problem. That happens quite a bit, actually.
Okay.
Sidebar. So now we got our answers. Does it make sense? I have no idea, but I know my math is solid, so we'll go with it. Notice my units again. What was height measured in? Feet. What was time measured in? Minutes. There are my units, feet per minute. Pregunta.
So you're saying that, like, you think it makes sense because you're confident in your math, what if you're not confident in your math? Is that what you said?
I would go with it anyways.
Just be like, yes, then would you get 1 point off? Not
Well,
2?
what answer? Yeah, we'll see you tomorrow. We miss you already.
Bye, Keenan.
Bye, Brad. See ya. What would you get as an answer that you would say that makes absolutely no sense?
Maybe if it was like in like the 3000s.
Yeah,
I don't know.
because the cone's only 12 inches tall or feet tall, so yeah, if you get something like 3,000 full, yeah, you made a mess in the yard and it flooded the neighbors. Okay, what else would not make sense for an answer?
A negative.
A negative wouldn't make sense because we're filling the tank, so the height has to keep getting bigger.
Something
You
in
can't fill the
minutes per
tank and
feet.
have the height go down. Okay, so even when you don't know if that's reasonable for feet per minute, there are still instances where you'll get an answer where you go, what?
So
Or if
like
it goes
you
up by
get a-
minute per feet.
There you
Then
go.
if you get a wrong answer, does that mean you have to like erase everything and restart it?
I wouldn't erase everything, I'd go back and try to figure out where you made a mistake. And more than likely, it probably came in with plugging things in, or in something like this in the sidebar when you solve the right triangle.
So, like,
Day
would you want us to like
31,
redo the problem?
30,
Like, would it be
30.
smart to redo the problem, or just say I messed up?
It will get
Probably 29.
Okay, so
Or not?
tonight, I would start taking a look at